So here in Chapter 9, we are going to study differential equations, which are just an equation that involves a function and its derivative, and we want to be able to find the function. So first, let's talk about some modeling that uses differential equations. So differential equation first, just some equation here that involves an unknown function and its derivatives. And recall that derivatives are interpreted as rates of change. So population growth models, where p is our function and t is time, that's population at time t. So those are modeled by differential equations. The assumption that we'll make in our population growth models is that the rate of population growth, so that's going to be a derivative, is proportional to the population size. So you'd write that like this: dp dt, that's the rate, the derivative, is proportional to p. And remember, that means the same thing as dp dt is a constant multiple of the population p. So k is our constant of proportionality. So k is also that growth constant, or the population growth rate. So what kind of functions p would satisfy this differential equation? So the derivative of the function is just a multiple of the function again. Well, if you take an exponential function and you differentiate it, if it's the right kind of exponential function, then you'll get the exponential function back again. So things that look like p of t is e to the kt. So if you take that derivative, you get e to the kt, and then times the derivative of the inside, which is this k here, which is k times p. Now, if k is greater than 0, then our population is growing. If k is less than 0, our population is dying. So that is the first and most important model for differential equations that we're going to consider. Now, we might ask, what do the graphs look like for this? E to the kt. Well, here's population on the vertical and time on the horizontal. And remember that exponential graphs start out growing slowly and grow faster as time goes on. So here's some possible exponential graphs. And then this value right here on the y-axis is your initial population. Now, a more realistic model is one where you have limited resources. So populations can't just grow exponentially forever. So we've got limited resources in any environment, even the entire Earth. So our assumptions here are going to be that the rate of change of population is proportional to the population. That's going to be if p is small. And the rate of change of growth of population is going to be less than 0 if p is greater than m, where m is what's called the carrying capacity. So that is the maximum amount, so think max when you see m, the maximum amount that the environment will sustain. So the model for this is something called the logistic equation, and it looks like this: dp dt is k times p times 1 minus p over m. So that's our differential equation, involves dp dt and p. M is a constant and k is your constant. What do the graphs look like in this case? Well, we've got p here on the vertical axis, t on the horizontal, and then this dashed line up there, that is the carrying capacity when population equals m, the maximum that's sustainable in that environment. So what happens is that these start out growing exponentially, but then as they get closer to the limit of what the environment will sustain, then they taper off and they become asymptotic to this line p equal m. So they can start a little bit higher, so they'll get up to the line quicker, but still asymptotic. And then if they start above population m, then they have to taper off. So either way, they're asymptotic to m. So here notice that it's going down from left to right, so the population is decreasing instead of increasing. And then the last model we'll consider is a spring motion model. So Hooke's law, which applies to springs, states that the force needed to stretch a spring is negative k times x, where k is your spring constant and x is the displacement from equilibrium. So the negative is just saying that the force is in the opposite direction of motion. So if you stretch a spring, it wants to pull back. If you compress the spring, it wants to spread out. And then Newton's second law, recall, says force is mass times acceleration, and acceleration is the second derivative of position x, or in this case, displacement. So we're going to consider a hanging spring model. So that's one in which the force due to gravity is exactly offset by the restoring force. So these two forces are equal to each other. That's how we get our differential equation. So the force due to gravity is mass times acceleration, and the restoring force, Hooke's law, is negative kx. And the picture here, we've got our hanging spring here, m, mass m on our spring, and then this is in the stretched state. So this length here, when it's hanging and not moving, that length is called L. That's the equilibrium length. And then if you stretch it, it's got a positive displacement x. So this mass at this position has displacement x, where x is positive. So x positive is stretched, that's going down. X negative is compressed, that's going up. So let's try to solve this differential equation and see what solutions might look like. So divide off that m on both sides. So it'll cancel on the left, and it comes down here underneath the negative kx. And then this is saying you take x as your unknown function, you take two derivatives of it, and then you get back a multiple of x again. So we want to know, what does that x, or x of t, look like? So what functions do you differentiate twice and you get a multiple of the function back again? Well, exponentials would work in there, like we had before, e to the kx, but springs are oscillating models. So think about sines and cosines here, because if you differentiate a sine here, you get a cosine, and if you differentiate cosine, you get negative sine. So in this case, since we're modeling springs, it's not going to be exponentials, but combinations of sines and cosines that make up this function x. Now note here that we've got a second derivative there, so that means that this is a second order differential equation. So whatever order the derivative is that you're taking, that describes the order of the differential equation.